We're doing a weak acid, strong base titration. Let's say in our Erlenmeyer flask. Okay, so there's our Erlenmeyer flask that we're titrating into. Let's say this time we have 30 mils of, I don't know, how about 0.150 molar acetic acid. That's the weak acid you'll be using in the lab tomorrow. Different concentration, but whatever. And let's titrate it with a strong base. So there's our burette. Let's titrate this with 0.110 molar sodium hydroxide. So that's what's in the burette. We are titrating 30 milliliters of a 0.15 molar acetic acid solution with 0.110 molar sodium hydroxide. Okay. And I want to get the pH along the way. We will need another piece of information. Since that's a weak acid, we're going to need the Ka. The Ka is 1.8 times 10 to the negative fifth for acetic acid. Buckle up, folks. Here we go. My first question to you is going to be how much or what volume of titrant is needed to reach the equivalence point. So go ahead and solve for that. All right. So this is where you use the MAVA equals MBVB formula. Molarity of the acid, 0.150 molar. Volume, 30 mils. Molarity of the base that we're titrating with, 0.110 molar. And we'll solve for the volume of the base needed. We need 40.9 milliliters of the base. So we're going to make a note of that. The equivalence point, where to make a note of that? We're going to make a note of that right up here. The equivalence point is at 40.9 milliliters of the titrant being added. So after we've dispensed 40.9 mils out of the burette, we'll have reached the equivalence point, okay? I got to erase this. That's why I wrote it down up there. And I want to remember where that is, and there's no way I'm going to remember that. Oh, we need a lot of space on the board. You're going to see why, especially when we get to that equivalence point. Oh, my goodness. All right, so part B, I want to know what the initial pH is here. And this is the first thing that makes this problem more difficult than the initial acid problem. Okay, and the first reason that this is now more difficult is because in the strong acid problems, okay, the concentration, because it fully dissociates, the concentration is the H plus ion concentration. Okay, however, since this is a weak acid, you got to go through that whole weak acid process. So the first issue is, what is the initial pH? So what is the initial pH before we add any titrate? Okay, this is a weak acid problem. We've done this, like this was the last class, right? Okay, on Monday. Okay, I want to know, you don't have to worry about any of this other stuff, just what's the pH of a 0.15 molar acetic acid solution. So you're writing out a dissociation equation for acetic acid. You're writing a mass action expression. You're making an ice table. Go ahead and solve for what the pH of a 0.150 molar acetic acid solution is. We haven't added any base yet. Take a minute. Right. So you should get to this point where 1.8 times 10 to the negative fifth, Ka, is equal to x times x over 0.15 minus x. We want to see if we can get rid of that minus x. I'm out of room kind of on the board. You'll see we're going to use a lot of this board to do these problems. But if I take that smallest initial concentration, 0.150, and I divide by 1.8 times 10 to the negative fifth, we get 8,330. So x is small. So we can get rid of that minus x. Multiply both sides by 0.15. We get 2.7 times 10 to the negative 6 equals x squared. Take the square root of both sides. X equals 0.0016. 0.0016. That is the H plus ion concentration. And now I can get a pH. pH equals negative log of 0.0016. And that is 2.78. So we are starting, if we compare this to the strong acid titration, this is more concentrated. This is 0.15. The strong acid titration we did was 0.1 molar hydrochloric acid. We're starting a much higher pH because it's a weak acid, right? So we're starting, in the zero. We're starting at, here's 2, there's 3. We're starting, somewhere closer to 3. So when you're doing a weak acid strong base titration, getting the initial pH is more work. Getting the initial pH is more work because it's a weak acid, and you got to do a weak acid problem. Okay, so we're starting there. Okay, I want to now add some titrants, and I want to talk about what's going to happen, and it's going to look terrible, and then we're going to get bailed out by the Henderson-Hasselbalch equation, but I don't want to give it too much away. So here we go. So I don't know, what is the pH? This is point C. After, I don't know. Let's do 10.50 milliliters of titrant is added. Cool. So now we need to write the reaction. Now we're adding the sodium hydroxide. The first thing we need to do is write down the reaction that's going to happen. So the acetic acid, HC2H3O2, reacts with the sodium hydroxide to make water and sodium acetate. Now that sodium is a spectator ion. So if you want to get rid of the sodium, you totally can. In fact, I usually do. Now we've added something. So when you add something, whether it to be a buffer or during a titration, that's BAA table time. So we need to make a BAA table. Water is pure liquid. You don't have to worry about it. So we need to fill out the before. There's only acetic acid in here. So none of that and none of that before. So we need to figure out, again, BAA tables have to be moles. We got to figure out how many moles of acetic acid are in here. So we take the concentration times the volume in liters. So 0.150 moles of acetic acid times 0.0300 liters. That's going to be 0.00450 moles. So we are starting with 0.00450 moles of acetic acid in there. Cool. And now we need to figure out how many moles of hydroxide we're adding if we add 10.5 milliliters of a 0.110 molar solution. So here we go. 0.110 moles of hydroxide per liter times 0.01050 liters. 0.11 times 0.0105. That's going to be 0.001155. Again, we'll do sig figs at the end. Moles of hydroxide that have been added. So I've got enough acid in here to cover that base. So the base will be gone. I need to subtract this from this. So 0.0045 minus that. That's 0.003345 moles of acetic acid that remains. And this got turned into acetate, so I now have 0.001155 moles of acetate left. Here is the difference. This is really important. In a weak acid strong base titration, the salt you make, okay, which is sodium acetate, which I just got rid of the sodium as a spectator on, that's a basic salt now. Acetate is the conjugate base of a weak acid, so that is basic properties. So this is going to affect the pH. So it looks like, what do I do, right? You know how to do it. Here's the good news. When you're titrating, until you get to the equivalence point, when you titrate a weak acid with a strong base, or you titrate a weak base with a strong acid, you are creating a buffer. I now have a weak acid and its conjugate base. This is a buffer, right? While you titrate a weak, strong titration, you're creating a buffer till you reach the equivalence point and kill all the acid. There's not a buffer anymore, okay? So we can get the pH using the Henderson-Hasselbalch equation. So all we need to do is turn these back into concentrations. And then we can use the Henderson-Hasselbalch equation to get the pH. It's beautiful. So we got to divide by the new volume in liters. So 30 mils plus 10.5 mils. That's 40.5 mils, right? So that's 0.045 liters, right? Did I do that right? Somebody yell at me if I didn't, because that would suck. 30 plus 10.5 divided by 1,000. That's 0.04050 liters. And now we're going to divide this by that same number. And we're going to get concentrations out of these. This is 0.0826 molar. I'm going to go to 3 sig figs. 0.001155 divided by 0.0405. That's going to be 0.0285 molar. And now I can get the pH using the Henderson-Hasselbalch equation. pH equals pKa. Take the negative log of the Ka. Negative log of 1.8 times 10 negative fifth. We've done that a bunch. That's 4.74, I'm pretty sure. 4.74. So 4.74 plus the log of the base, 0.0285 divided by the acid concentration, 0.0826. That's 4.27. So you can see it's going up faster than the other titration, although you do get this kind of buffer region where the pH isn't changing too much, right? It's not super duper drastic. We call it the buffer region. We'll see that tomorrow in the lab. Okay, now what do? We added some titrant. Takes 40.9 mils to get to the equivalence point. We're at 10.5. I want to do a very special point. The next point is going to be halfway to the equivalence point. So point D, I want you to put a star here, and you're going to see why this is so special. This is the halfway to the equivalence point. So the equivalence point is at 40.9 mils, right? So if we do 40.9 divided by 2, that's 20.45 mils. Here's what I want to do. I want to get the pH after 20.45 milliliters of titrant is added. So again, I got a whiteboard. It's so awesome. Love it. I want you to try to fill in the BAA table for that. Again, the before doesn't change. Okay, but now I want you to fill in the amount of hydroxide being added. That's going to change. And then see if you can get the second A row done. Okay, we're adding 20.45 mils of titrant. It's 0.110 molar. Go ahead. See if you can't fill in the rest of that BAA table. So if we take the concentration of the titrant 0.110 times the volume, we're adding 0.02045. We are adding 0.00225 moles of hydroxide. Now you're going to see here in a moment what makes this so interesting. We have more than enough acid to cover it, so no hydroxide left. We're going to subtract, and here's where it gets interesting. We get the same value, 0.00225 moles, the same amount of acetate, and the same amount of acetic acid that's left is equal to the same amount of its conjugate base that I've created. So what do I have here? Well, let's stop and think about it and see if we can't make a prediction. I have the same amount of a weak acid as this conjugate base. I have a buffer, weak acid, conjugate base. They're the same amount. This is going to be a 1-to-1 buffer. And if you remember from yesterday, what's significant about a 1-to-1 buffer? Well, you see here in a second. Maybe you can make a prediction about what's going to happen. It's still a buffer. We can use the Henderson-Hasselbalch equation here. But before we use the Henderson-Hasselbalch equation, it's got to be molar. So we need to divide by the new volume in liters. So 30 plus 20.45, 30 plus 20.45, that's 50.45. We're going to divide by 0.05045 liters. And we get 0.0446 molar. And now we can get the pH using the Henderson-Hasselbalch equation. So pH equals the pK, 4.74, plus the log of the base, 0.0046, nope, 0.0446 molar, divided by the concentration of the acid, 0.0446 molar. And what do you get with a 1-to-1 buffer? When you have a 1-to-1 buffer, the amount of acid and base are the same. The log of 1 is 0. The pH is the pKa. When you are halfway to the equivalence point, the pH of the buffer is the pKa. I cannot emphasize how important that is. That when you are halfway, which was 20.45, we are at the pKa at that point. This is the pKa. Halfway to the equivalence point is the pKa. So we did the initial pH. We did the pH at a point leading up to the equivalence point. We did halfway to the equivalence point. Okay. The worse this gets, the absolute worst these problems get, is at the equivalence point. So we're going to do at the equivalence point, and then we're going to go past the equivalence point. So we had 2 more points to do tonight, right? At the equivalence point and past the equivalence point. Okay, so hang in there. This is as bad as it gets. E at the equivalence point. We got this. All right, folks, here we go. Point E, we are going to get to the equivalence point. I want the pH after 40.90 mils of the sodium hydroxide is added. Oh, boy. I'll give you a second to make that table. We're going to do this one together because this one is no joke. The equivalence point of a weak strong titration is a lot. It's a whole page of paper right there. So We need to figure out how much hydroxide we're adding. Now, if you're smart, we're at the equivalence point. So we're adding the same number of moles, right? But let's just prove it. 0.110 molar times 0.0409, right? Pop that in your calculator. 0.11 times 0.0409. That's going to be 0.00450 moles. Why is this significant? Well, at the equivalence point, as the name suggests, no acid left, no base left. They're equivalent. And this has all been turned into the basic salt. So now what? Well, I need to get the concentration of this basic salt. And then the equivalence point becomes a basic salt problem. Becomes a basic salt problem. So the basic salt problem that we practiced earlier near the beginning of class tonight, okay, that's now in the middle of this titration, right? So let's turn this into a concentration here quick. We're going to divide by the new volume. So 30 plus 40.9, that's 70.9. So we're going to divide this by 0.0709 liters. And we get 0.0635 molar acetate. And now we have to go through the whole ice table rigmarole. Here we go. I got to erase this because I'm not going to have room. So now I have to say, well, okay, I've got a bunch of acetate in here, and that's it. What's that acetate going to do? Well, acetate acts like a base because it's the conjugate base of something weak. It reacts with the water to make HC2, H3O2, and some hydroxide. I can now make a mass action expression. It's a base, so Kb equals the HC2, H3O2 concentration times the hydroxide ion concentration divided by the acetate ion concentration. Now, I make an ice table. The initial concentration of the acetic acid, no, the initial concentration of the acetate, oh my goodness. The initial concentration of the acetate is that 0.0635. There's no acetic acid or hydroxide in there until it reacts. That's going to go down by X. These go up by X. Now I'm going to plug these values into the Kb expression. But I need a Kb. Now I have the Ka of acetic acid. So I need to turn that Ka into a Kb. So that's going to be the Kb is going to be Kw divided by Ka. So 1 times 10 to the negative 14th divided by 1.8 times 10 to the negative 5th. That's a Kb value of 5.6 times 10 to the negative 10th. So now we plug that stuff in here. 5.6 times 10 to the negative 10th equals X times X over 0.0635 minus X. At this point, we want to check if X is small. It is going to be small. 0.0635 divided by 5.6 times 10 to the negative 10th. You can put it in your calculator, way greater than 500. So X is small. You can get rid of the minus X. Multiply both sides by 0.0635. we get 3.53 equals x squared. 3.53 times 10 to the negative 11 equals x squared. Take the square root. X equals 5.94 times 10 to the negative 6 molar. Let's pause there. We're almost done. What did we just get? We just got the hydroxide ion concentration. So what can we do with that? Well, we can get a POH. So the POH is the negative log of that concentration. That's 5.23. I want the pH. So 14 minus 5.23, and we're going to have just enough room. It's amazing. 8.77. So what do we find? What we found is the equivalence point. So you got this graph, right? It's doing one of those. And we find that the equivalence point is actually basic. In a weak acid strong base titration, the equivalence point is basic. 7 is, here. We're above 7. It's basic because the only thing present at the equivalence point in a weak acid strong base titration is a basic salt. So it's basic, right? So we get 8.77. Okay. That is a lot of work. It's a BAA table. Okay. And then it's an ice table. Right. And it's, oh my gosh, and then you got to turn the KA into a KB, all that stuff. Okay. But it's totally doable. It's like taking it's taking a salt problem and putting it together with a titration problem. Okay. We can do this. This next one is really fast. And here you can't be jealous of me anymore because I had to erase my BAA table. So I'm in the same boat you are, folks. So we need to write the reaction out again to make our BAA table. So the acetic acid reacts with the sodium hydroxide or hydroxide to make water and acetate. And then we made the BAA table. And before we added anything, it was 0.00450 moles of that. Now we need to figure out how many moles of hydroxide we're adding. So we take the 0.110 moles of sodium hydroxide per liter, multiply by the volume. We're adding 50 milliliters. That's going to be 0.0055 moles of hydroxide. And we'll pause here, talk about where we're at. So now, I obviously do not have enough acid to cover that. All of the acid is gone. It gets turned into the conjugate base, which isn't actually going to matter here. We'll talk about why in a second. And I'm going to have 0.055 minus 0.045, right? I'm going to have 0.0010 moles of the hydroxide left. Now, what do we have? We have an excess of a strong base and some weak base. Here's the good news. Unless you're taking analytical chemistry, that weak base is not going to affect the pH once you add an excess of the sodium hydroxide, because now you have a strong base in excess. That is small potatoes. Okay, and if you take analytical chemistry, they'll make you maybe add in what we just did. Okay, like, oh, don't worry about it. Okay, all you need to do when you get past the equivalence point is you need to divide this by the new volume, get a concentration of hydroxide, and then it's just POH, and then 14 minus that to get the pH. Watch how beautiful this is. 30 mils plus 50 mils, that's 80 mils. So we're going to divide this by 0.0800 liters. that's going to be 0.0125 molar hydroxide. And now I can get a pOH. pOH is the negative log of that. That's a pOH of 1.90. And then 14 minus that, that's 12.10. The pH is 12.10. So you see, once we get past the equivalence point, it continues to skyrocket, and you're going to get 12, and then it'll kind of curve out.